Okay, good morning. Today the microphone is not working, so I hope you can hear me also in the back. Yes? If I start talking too quietly, just let me know. So welcome today's lecture. It's actually the last lecture that I will be giving today, because next week, which is the final lecture, is going to be a guest lecture again. It's going to be a researcher from a similar research laboratory working on simulations on the heart. So she will give you some insights in scientific computing and the tools that we use in scientific computing. And hopefully she will also show us some cool results of her heart simulations. Okay, but today's topic is machine learning. And how many of you have worked with machine learning before? Some. Okay, perfect. So this is going to be a kind of a quick introduction into machine learning and how you can do machine learning in Python. And I don't expect you to understand all the details of machine learning, but I do want to show you that with the modules and the knowledge that we've now learned in part of this course, it's possible for you to run some simple machine learning models and play around with them. So, I mean, machine learning is kind of a hot topic at the moment, and I think this graphic here demonstrates it quite nicely why it is so popular. So, I mean, there's two people sitting here, and the guy back on the computer says, when a user takes a photo, the app should check whether they are in a national park, right? And then the lady, the programmer, says, sure, it's easy. We use some GIS, which is the Geographic Information System. Look up, give me a few hours to solve this, right? So it's a problem of simply getting maybe some GPS data and figuring out where that person is. And then the boss in the back says, and check whether the photo contains a bird or not, right? Very simple question to ask, but then the answer is, I need a research team and 5 years, right? So these type of questions, even though they seem quite similar, right? The second one is extremely difficult from a computational science perspective. And machine learning is one of the promises that we have that can solve these type of questions. So, but before we dive in, we should talk about what machine learning is. There's many different definitions out there. I've posted one of them. It reads, machine learning is the semi-automated extraction of knowledge from data. Okay, so there's three main components that we need to look at. First of all, machine learning is about data. Right? The data is really the basis of machine learning. If we don't have data, we can't do machine learning. Then it's extraction of knowledge. So we want to gain additional knowledge from the data that we are working with. And the last part is semi-automated, meaning that so it's not manual. We don't want to manually look at the data and figure out how to extract the data. It should be automated. But it also shouldn't be fully automated, so that we do expect some user expertise and user interaction for this to work. So semi-automated extraction of knowledge from data. So now, in order to, of course, this is an extremely wide definition, so now we need to break it down a little bit so that we can become more concrete. And on the largest level, the way we can break down machine learning methods are by defining supervised versus unsupervised machine learning. And the supervised learning is essentially about making predictions using data. So you have some data and you want to make a prediction. So I give you some examples on a very rough scale, right? So you have some input data, then you have your machine learning model, and then, for instance, you want to decide if this data is talking about apples or is talking about pears, right? So that's called a classification machine learning problem. You have some data input, and you want to classify it into different sections. And so the second supervised learning type is a regression problem. So there you also have some data, here the blue data points, and you want to make a prediction for data value that you have not seen yet. So a typical example could be, imagine you have some information about the person's life, and you want to predict the life expectancy of that person, right? So your input data is everything from, is that person smoking and drinking alcohol or doing sport? And the output is a number of the life expectancy. And so the main difference here between these classification and regression problems is that the output that we're talking about in classification is a finite number of outputs. You often you have, in this case, you have 2 classes that we're talking about, but you might also have 1 million classes, but they're always limited. While for regression problems, these are always problems where you have a floating point value as an output, right? So infinitely many choices to make rather than a finite number. Does it make sense? And then the third category of machine learning is unsupervised machine learning. And there you try to tackle problems where you have a lot of data, but you don't really know. You want to ask question on what does this data actually contain? You don't know anything much about the data, and you're asking, can we maybe categorize this? Can the algorithm categorize this data for me? So a typical problem is, for instance, maybe you have some galaxy stars, right? And you're asking, you have loads of information about all these stars, and you're asking the algorithm, can you kind of cluster all these stars for me without me having to define on how to do that? So in a way, the way you can visualize this is that you have a 2-dimensional data points here, loads and loads of data points, and the unsupervised machine learning method can color them for you based on some similarities between these data points. Okay, I'll show you in a practical example in a second. Here's some questions for you to decide if these problems are supervised or not supervised. Let's look at the first one. Given a photograph of a person, identify the person in the photo. This is, for instance, what Facebook does, right? When you upload a photo, it suddenly tells you, oh, your friend blah 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 is on this photo. So if you're asked to solve this task, would you use which type of machine learning method would you use? Any idea? Yeah. Yes, it's a supervised problem. So we assume that we have already. Yeah, it's a supervised problem, but can you be more specific?
You would need to have a lot of pictures of this person so that the algorithm can say for sure with a high probability that the new picture is the same.
Yeah, but is it a classification problem or a regression problem?
Classification.
Yeah, so it's a classification problem because there's only a limited number of people on the Earth that that person could be, right? So then the second problem, given some live traffic information, predict the travel time of a specific route. What would that be? Yeah?
Regression problem?
Yeah, it's a regression problem. So it's again a supervised problem, and the outcome variable in this case here is the time, which is not a finite number, right? But it's It's a floating point value. Then problem number 3. So if we had solved this in 2009, we would have won $1 million. And now it's unfortunately not worth that much anymore. But the problem was given by Netflix. It was a very young company back then. And they asked the question, given a list of movies a person has watched and their personal rating of the movie, recommend a list of movies they would like. Okay? Which type of problem are we looking at here? Yeah? Could be unsupervised, but you do have some information about what that. I guess it could be both supervised and up. Yeah, yeah. But you do have kind of you know what the person has watched, and you also have the personal rating, right? In that case, it would be somewhat the labeling, maybe. But it's certainly also it is somewhat kind of a maybe a classification problem, right? Because you want to identify the movies that that person is likely to watch next, right? Okay, but let's look at the last one. That's a fun one. So given a mixture of 2 sound sources, for example, a person talking over some music, separate the 2. Right? This is known as the blind source separation problem. Any idea what that would be? I mean, so again, there's maybe it depends a little bit on how one wants to tackle this. This can be a supervised one, but it can also be maybe an unsupervised one. But if you want, so this is a fun example. So just recently, there was a submission on Hacker News. Do you know Hacker News? Some of you do. So it's a website where there's all kind of fun stuff for us. It's a forum essentially, and they've posted this. So they posted a solution to exactly that problem, and they also posted the source code, which you can find here. And let's see. Let's see if this works. Let's see. Can you hear anything? I can't. Okay, oh, this is horrible. Someone has messed the sound system here. Okay, can you hear that? Okay, so okay, that was the original sound. Okay, so now they've applied this machine learning method to separate the singing from the guitar in the background. Okay, so now we're going to listen to the output, what the machine learning method identified as the voice.
Hey, it's Bob from the office down the hall. It's good to see you, buddy. How have you been?
It's quite cool, isn't it? Let's listen to the rest. Okay, so I just wanted to show you that these are kind of quite cool applications that one could imagine using these kind of techniques. Okay, so I'll be mostly talking about supervised learning for this lecture. Essentially, maybe we look at an unsupervised a bit later on. So how does supervised learning work? So essentially, supervised learning consists of 2 main steps that you need to perform. The first step is that you need to train your model. And the second step is making new predictions of your model, using that trained model. Okay, so let me explain to you. I just want, maybe let's explain the second example, the second step first. The second step is represented down here in this graph. And essentially, we're going from left to right. So you want to make a new prediction using the data. Let's be concrete. Let's say you want to predict the weather of tomorrow. Okay, that's the prediction that you want to make. So in order to do that, we assume that we have some input data. So it could be maybe the information of the weather stations that we have, the temperature and the pressure of the of various sensors that we have. So we have this as raw sensor data. The first step that we need to do is that we extract the main features of these sensors, right? So maybe typically we're not interested in all the different details. Maybe we even have some information from webcams. So maybe we want to extract kind of the main features of all this input data. And then what we end up with is that we have a long vector, essentially long NumPy vector later on, containing the data as pure numbers. And then we pass it into our machine learning model, which has been trained already from step number 1. And then the output will be the prediction that the machine learning model gives us, right? In this case, it would be the weather of tomorrow. Okay, so this is how we're going to use the machine learning model once it has been trained. But of course, we first need to train it. So how does the training process work? This is represented here by the blue section. So for the training, we again need data. And in this case, we not only need a single data, but we actually need an entire collection of data. And so for this weather example, it would be probably be historical data, right? So maybe we've collected data for the last 20 years of all these sensors and maybe webcam images. In addition to this data, we also need to know the outcome, right? So these are called labels. And this is what the weather actually was on the next day. So we need a collection of the data and the correct result for these. These are called training examples because these are examples that tell us what the input and the output was. So okay, so what do we do then? We from all this input data, we extract exactly the same features as we've done it already for the prediction. So now we have a set of features and the corresponding labels. And then we feed both into the machine learning algorithm, and this is going to be called the training process. So this part here is where the machine learns the relationship between the features and the outcomes. And the result of this learning process is the predictive model that we use later on for the predictions. Does that make sense? So, you as a machine learning engineer, you have some options when you're supposed to build such a system. And the most important choices that you can make is which features do you want to extract from the data that you get, right? You probably get loads and loads of data, and your task is you need to somehow convert this input data into a feature vector. And this is something that is not automated, but that you have to do and decide as a machine learning engineer. The second big choice is which machine learning method do you want to choose, right? There's many, many different ones out there, and they will all behave differently and perform differently. And then finally, we need to be able to evaluate the quality of the entire prediction model. So we need to learn on how to check and hopefully improve the quality of our trained models. So this was the theory. Now we come to the practical part. We will do exactly what I've just talked about in a Python module called Scikit-Learn. So it's Scikit-Learn is a machine learning module in Python. It implements many of the classical and also some of the more modern machine learning methods. And the nice thing about Scikit-Learn is that there's well, I would say the three main things. First, it's open source, so it's very easy to use. Secondly, it has a common user interface for all these different methods. So you essentially, once you've done the data preparation, it's very easy to swap out one machine learning method with the next one. Right? So you can experiment very quickly. And finally, it has very well chosen default values. So even if you're not an expert with that specific machine learning method, typically it's a good start to just try it out with the default settings and see how it behaves. And then you can always tweak and improve it further. So then the main things that one typically needs for such a setup is, of course, Scikit-Learn. And there's some, the website is quite informative. Matplotlib is, of course, important because we will often, it's very important to not just apply the framework that I've just shown you blindly, but it's very important to actually look at the data and understand the data in order to be able to extract useful information out of it. And of course, plotting there will be essential. And then pandas that I've taught, was it 2 weeks ago? It's important to actually read in the data, clean it up, and prepare it to be used for the machine learning. So then installing Scikit-Learn is straightforward. If you have Conda, you can just install it using Conda install. Same with pip3. And then if everything works out, you should be able to import it. So the module is called sklearn. So you want to type in import sklearn. And then I also need to import matplotlib because I'll use it in a second. So now we need to understand how Scikit-Learn works internally. And okay, so the main data structures that we will be working with in Scikit-Learn are two-dimensional arrays to store the data. And it's two-dimensional, well, I'll explain in a second why. So the Scikit-Learn is based on NumPy, so we expect this data to be in a NumPy array, which we already know. And so now let's understand why Scikit-Learn expects a matrix or a two-dimensional array. So the size of that array is number of samples times number of features. Okay. So number of features I already said. Number of features is the one data is represented as a feature vector. Okay. So it's one vector. But remember, for the training process, we are not operating with a single data, but we is operating on an entire data set. So and these are called samples. So we have a matrix where each column represents one data, the features of one data, and then we have many of them. And in total, we have number of samples, many of them. Okay. So each number of sample represents one example that we can use for the training process. So this could be a document, a picture, maybe a sound or video, or anything that you received as a data set. And then the features, this is the main features that we extracted from each example. So here it's important to remember that the numbers of features have to be constant across all examples. So we can't, in most cases, we can't add more and less features for each example. It has to be fixed. But it can be, it has to be fixed, but it can be very, very large. Right? So if you want, you can have millions of features. So then you will have a very, very large matrix. But numerically, that's fine as long as you use the right algorithms. So now let's look at a concrete example. So our task, and this will follow us essentially through most of the lecture. So the task that we want to solve here is we want to learn a machine we want to develop a machine learning algorithm that predicts the type of an iris flower. So an iris flower, they look like this. And it turns out there's actually 3 subcategories of iris flowers. They're all shown here. And we want to develop a method that distinguishes these types of flowers. So this is a classification problem, right? Given a new flower, we want to classify it into one of these 3 subcategories. So they're called, because this will come up over and over again, so the names are Iris setosa, which is this guy here, then Iris versicolor, which is this one, and Iris virginica, which is this one. Okay, so the goal is predict the species of an iris using some measurements that we've taken. And it's a supervised classification task. So now the question is, which type of, so you are asked, you're now the machine learning expert, right? And you're giving, maybe you have a biologist working for you, and he now goes out into the field and collects data, right? And your task is now to decide which kind of data he should collect, right? Because you need to develop these feature vectors. Right? So any ideas on which kind of features we ask the biologist to collect for us? Yeah? Yeah, some sizes. For instance?
What about the length of the yellowish pattern of the petals?
Yeah, so that's a good idea, right? So maybe measuring here the length of the yellow part.
Maybe like how sharp the turn is, like, you know, how
Yes.
it bends.
Yeah, maybe how sharp it bends here. That could be interesting, right?
Color?
Color, yeah. Yeah. But I mean, you see, you have exactly the right thinking process, right? So we need to identify some kind of features which hopefully will help us to distinguish these 3 categories, right? So, yeah. And so we come up with a bunch of them, and of course, we can't have too many because it takes a lot of time to collect them. And they need to be fixed, so we need to be able to collect them for all the plants. Okay, so right? I mean, you had really good ideas. So luckily for us, someone has already collected some data for us, so we don't need to do it. And the data that they've collected is the following. They've measured the sizes of the leaves of these large leaves, which are called the sepals. They're the down-hanging leaves. And then also the petals. These are the leaves that are smaller and that are going up. And for both of them, they measured the width and the height. Okay? So this is the data that we have, and so hopefully this will be enough to make some good predictions. And maybe if we can't manage, then we need to collect more data. Okay, so it turns out in this iris data set is actually a default data set that Scikit already has as part of it. So we can just load it in. We can save kind of all the data preparation stuff. And the way you do that is you have this in Scikit-Learn, you have this datasets package, and inside there you have this load iris function. So I can load it in. And so this data now contains the following. We will have the features of the iris set. So for a bunch of irises, we will have the sepal length and sepal width, and the petal length and petal width. And then we also have another data set that contains the correct classification of the iris flower. So for each of these examples, we will know if it was an iris setosa, iris versicolor, or an iris virginica. Let's look at this data. So remember, here I loaded the iris data in a variable called iris. So now we have this iris is actually a dictionary, and it contains the key data, and that contains the feature sample matrix. So you can see this is a two-dimensional array. I have a double bracket here, and then you can see this is a matrix, right? And the dimension of the matrix is it has 4 columns, and each it has 3 columns, and each row here represents one data. So the first item here, each of these numbers correspond to either the length and the width of the petal and the sepal. Right? So here, this is one flower, the first row. The second row is another flower that we've measured. The third row is another flower that we measured, and so on. So this is a long matrix representing all the different flowers that have been collected. And so in total, we can look at the shape. And so we can see in total, we have information, or we have the measurements of 150 flowers. And for each of them, we have these 4 features. So we can, of course, here it isn't quite clear which features this actually corresponds to. So there's another key in the dictionary called feature names. And that tells us that the first column here represents the sepal length, the second one the sepal width, the third one petal length, and the last one petal width in centimeters. So then the third thing that we need is the correct labels or the target values of all these examples. And this is contained in a key called target. And here you can see these are essentially the outcomes of the data that we've collected in the 3 categories. And the categories are here represented by 0, 1, and 2. So the first bunch of examples that we had in our data set were all category 0. Then we had all the data of category 1, and then all of category 2. And again, because the target here is just numerical, so it's not very informative, but there's also the key target names that then tells us that and everything that represents 0 here stands actually for the class setosa, iris setosa. Everything that corresponds 1 is an iris versicolor, and then the 2 represents a virginica. Does it make sense so far? Good. So now in summary, we have really what the machine learning model cares about, and the only thing that we need is this iris data. This is our matrix containing 150 samples, 4 features. An iris target. This is a single vector containing the label types or the targets for the 150 samples that we have. So now, as a very first step, before we start using fancy algorithms to make predictions, it's a good idea to look at the data and see what it means. To look at it because you already get a feeling on how realistic it is to classify the data. And a good way of, so the problem of visualizing this is that it's a 4-dimensional data set, right? For each single flower, we measured 4 values. And so in principle, we would need a 4-dimensional plot. So that's difficult. But what we can do is that we just visualize 2 out of the 4 dimensions, right? And that's exactly what I've done here. So what you see here is I've picked 2 of the features, the sepal length in this case and the petal length. And then I've plotted the different, the data set that we have. So, and I colored them according to the iris type. Okay? And so what we're looking here is now, what we want to see here is, we want to see that we want to see some kind of separation between the different classes visually here, because that tells us that hopefully the method should be able to classify them and distinguish them quite clearly. Okay, and so there's hope here, especially for the setosa iris type, right? You can see the essentially, right, if I were asked to classify it, I would say the setosa iris type always has a petal length that is smaller than 2.5, while the other iris flowers have a larger one, right? So, and but you can already also see for the versicolor and the virginica, there's more complicated because there's clearly an overlap here, which makes it not so easy to separate the two, right? And then, of course, we can start looking. So here I have these two variables that allow me to specify the features that I want to visualize. So maybe if I pick two other features, so again, here, this didn't help so much. Red and gray is quite similar. So maybe we can visualize feature 1 and 3. Yeah, also doesn't help so much. So you can see, just by looking at these plots, you get a feeling of the data, and you will also get a feeling maybe of which parts are going to be easier to classify and which parts are going to be probably harder to classify. Okay. So, summary so far, we have 150 observations. We have 4 features. We have the labels, which is going to be the species of the iris, and we know that we have a classification problem. So now the next step is we need to decide on an algorithm that we want to use, a machine learning algorithm that we want to use for this classification. And for our case, and well, there's many algorithms out there, and I'm going to show you a guideline later on how you can choose a suitable algorithm for your problem. But I want to show you at least one algorithm, and I want you to understand one algorithm. And it's a very easy one, so it's relatively easy to understand. It's called the k-nearest neighbors classification. Okay? And the way it works is, the input of the algorithm is a new vector containing the measurements of an iris flower. So 4 numbers containing the petal length and width and the sepal length and width. Okay? The output of the algorithm is the class of the iris flower. So either 0, 1, and 2. Okay? So what does the algorithm do? Well, it has one parameter. It's the value of k. So k is a positive number, 0, 1, 2, 3, that the user has to choose. Okay. So then what the algorithm does is, this iris flower can be placed somewhere in our 4-dimensional space, right? It's a point in the 4-dimensional space. So now what we do is, we have loads of examples. We have this data set of examples that we've collected before, right? What we do is we find the k closest examples that are to the data point that we got as an input, right? So the k nearest neighbors of the data point that we see as an input. So then we have k data points of which we know the labels from, because it was this is example data. And so now we can look at the example output and just pick the one that is most popular across these. And that's our returned class. So to make this more concrete, so let's fix k to 1. So let's go through the algorithm again with k equals 1. So you get a new point in a 4-dimensional space. Then you find the nearest data point in your example data. You look at which class was that, and you return that class. Does it make sense? I visualize it just so that you that it hopefully becomes clear. So let's reduce it to 2 dimensions, and let's say this is the data set that we're talking about. So we have red dots, we have 3 classes, red, blue, and green. And we want to use the k-nearest neighbor classification. And so let's say the new input value is here. Okay, this is you're asking the k-nearest neighbor algorithm, which class does this point here have, a new input value, right? So what you do is you find the closest neighbor of that point, which is going to be this red guy here, and you return red as a class, right? Because that's the value here. Okay, it's as easy as that. And then if you have 2, let's say maybe you're down here, right? And you set k equals to 3, then you find the closest 3 neighbors, and 2 of them are blue, and only 1 is red, so your answer will be blue. Okay? So here's for this data set. This is a common visualization of how the algorithm does. Essentially, what I've done here is for every point in space, I've asked in this case, the 1 nearest neighbor classifier, how you would classify that data point, right? And so you essentially get this map of classes. Okay, and then of course you can start playing with the k. You can set k to 5, for instance. And then in some cases, you might get some gray values where it's actually not clear. Maybe there's, no, actually that doesn't make sense if you have 5. So in these cases, right, you might have, you probably have 2 blue ones, 2 red ones, and a green one, right? So then the output might be either red and blue. So it's not clear. And then it just marks it as gray. Another interesting aspect of when you move, so for the 5 nearest neighbors classifier, you might actually, you might get a green dot that is completely isolated, completely by red ones. So even though maybe your new data point is right next to a green one, it will still be classified as red because you have 4 red neighbors around it, just so that you're aware. Okay, I think that's, let's stop here and let's start again in 15 minutes.